students, welcome to Year 9 Science and Unit 1 Atoms and Stuff. And this is our 6th video, and now we're going to break down our look at the model of the atom by specific scientists who made a serious contribution or a significant contribution that moved our understanding of the model forward. So in this video we're going to focus on J.J. Thomson. What we're going to do is build up a little picture of the atomic structure in terms of some of those very important subatomic particles, the protons, the neutrons and the electrons, and we'll see what contributions different scientists made along the way. So J.J. Thomson was an English scientist who lived in the late 19th, early 20th century, and he based his understanding of the atomic model on his experiments with cathode ray tubes. Now hopefully you'll get the opportunity to have a look at a cathode ray tube in the laboratory, and particularly the interaction between the beam and things like magnetic fields. A number of experiments were done on the nature of cathode rays and how they interacted with magnetic fields, the energy that they had, and also the fact that they traveled in straight lines. And all of these were important qualities of these particular particles, which we now refer to as electrons. So I guess another way to look at cathode ray tubes is as beams of electrons, and you can see there are two electrodes at either end of this fluorescent plate, and you can see that the little beam of rays are striking that fluorescent plate, and so we can actually see where they are. And it also means that if we use magnetic fields to move that beam in any way, we can actually see the beam moving up or down relative to the plane of which it's moving. So if we bring a magnet close to this electron beam, then we can actually see the electrons being influenced by the magnetic field as they move relative to their straight line position if we have no magnetic field in place. So again, something that hopefully you'll get an opportunity to look at in the classroom. Now what happened with that discovery of this beam of particles was that it changed our understanding of the atom. Remember, Dalton's model was based on a solid lump, and therefore different types of lumps for different elements, but nothing specific that was different. He knew they were unique, but he didn't really know anything more about them. Now we know that there are these negatively charged particles, and that these negatively charged particles can flow. They can move from one place to another, from one electrode to another through empty space, through a vacuum, which is what's created in a cathode ray tube. Now Thomson also realized that if atoms were neutral, then any negative charges must be balanced by positive charges. So we had to have a balance of negatives and positives. Now his solution for this was that the electrons were separate particles, so they were kind of like little plums or little currants, little raisins, and they were sitting in this positively charged lump of material, which conjured up this idea of fruit in a plum pudding, or fruit in a pudding. And hence it's often referred to as Thomson's plum pudding model of the atom. It's characterized by these electrons, which he knew are now present, and he tried to modify the model to take account of these negative electrons, but he also had to take into account the fact that atoms being electrically neutral means those positive charges must be balanced with negative charges somewhere else. So this is Thomson's model. You can see it's kind of the Dalton lump with a few little extra things stuck in, and obviously these things that have been stuck in are electrons. And they're the negatively charged particles, and they are responsible for all of that behavior we saw around cathode tubes. And the lump itself is positively charged, and there's enough positive charge in there to balance the negative charges created by those electrons. Now this was great because we took into account protons and electrons. We realized there were positive and negative charges that were there. We didn't really know them as protons. We just knew that they were positive charges within the atom somewhere. But it didn't explain a very important observation that came not long after, which was in the work of Ernest Rutherford. And that taught us a lot more about the nature of the atom. But of course, Rutherford's a significant player himself, and so he gets a separate video. So thanks for watching.